It's better than bad. It's good. So, all right, excellent. Okay, but now, 2 to what power equals 6? Logarithms. Logarithms allow us to solve for unknown exponents by changing around what are called bases. Logs allow us to do that. Show us how. Yeah, you don't have to write those out. But anyway, you have to find the value of this. You have to define something that's called the logarithm. And logarithms deal with what are called bases and exponents. So you get this thing of log, what's called log base b of y equals x, which means b to the x equals y. Excuse me. Oh, that yours wrong. Getting it again. It just doesn't go away. So the way you say this is you say this is log base b of y equals x, or b to the x equals y. Now, the log of y with base b is how the book kind of goes through it. These bases, basically, you can switch them, you change them. There's a couple of properties we're going to have with them. It's one of those new math things that you've probably never seen unless you've taken the ACT, because it's on. I'm pretty sure it's on there. But there's they didn't talk about equivalencies, did they? Or did they just say, hey, what does this value equal? Oh, you could have put it in your calculator. There's a button. I think it's alpha window. There's a log button. That log button's different. Okay. There's that log, and I'll explain to you what that log button is as we get going and all that. So there's a bunch of different things to be able to do. So anyway, what we do here is we're going to look at. They also have these 2 properties, and this is kind of where everything kind of stems from. You have 2 properties of logs. Log base b of 1 equals 0, because b to the 0 equals 1. Anything to the 0 power always equals 1. Anything to the 0 power always equals 1. So what we write it in terms of logarithms then, we say that log base b of 1 equals 0. So you can have, we know that 4 to the 0 is 1. You guys agree with me on that? If I wrote that in terms of the logarithm, then it would look like this. Log of 4 of 1 is 0. Right? That's what that looks like. That's an equivalency. And then you also have the other property you'll see a lot of is log base b of b is 1, because anything to the first power is itself. Anything to the first power is itself. So if I wrote log base 5 of 5, it would have to equal 1, because 5 to the first is, yeah, they work back and forth. They work back and forth. Excuse me. That's fine. So this idea of logarithms are going to let you solve for exponents. You see this when we get later on in a chapter of sequences and series. There are ways of working with geometric sequences that you have to sometimes figure out what the exponent is, how many times something is occurring. So you have to use the logarithm to be able to solve for an exponent. It's as it seems very technical, but in the long run of working with these things, in the years we've taught it, it is brand new. But for some reason, you guys do pretty well at it. It's like, oh, but it all stems from these two properties, and if you can remember those, it's all good. It's long. It's long. So here, we'll write out going from log form to exponential form. It's kind of what we practiced with this to start with. We go from log form, exponential, then we'll go from exponential to log, and we'll go back and forth. So if I say log base 2 of 32, if I wrote that as an exponent, what would it be? 2 to the 5th equals 32. Because you're rewriting the, let me write that up too on the side. Okay. All right. Log base 5 of 1 equals 0 because, well, how would you write that as an exponent? Equals. Good. Log base 10. Log base 10 is your standard log base. On your calculator, the button that says log is in base 10. That is your standardized way of doing it. A lot of when this text was written, they didn't realize that calculators were coming around that were able to change the bases in the calculator. So there was formulas to said change, what's called change the base on there. So sometimes you will see this written as just log of 10 equals 1. If you don't see a base next to a log, you don't see a base, it is implied that it is base 10. Okay. It's kind of like if you have a variable with no coefficient, it means the coefficient is 1. It's the same basic idea there. They just won't write it as log base 10. So log base 10 of 10 is the same thing as saying log of 10. Just want to show you guys that. So log base 10 of 10 equals 1 means what exponentially? How would you write it? Pretty easy. Yeah? It's a lot of just switching the forms back and forth. Now, when they start throwing decimals at you, I want you to start thinking of exponent rules, especially when you see the negative. That means, what is 0.1? 1/10, isn't it? So 10 to the negative 1 is a 10th. So you'll see them written as decimals, but you'll also see them written as fractions as well. And you can have fractional bases. Log base 1/2 to the negative 1 equals 2 because of your exponent rules. Oops, sorry. All right. Exponent rules come back into play, things like that. It's pretty, shouldn't be too crazy. Okay? Throat second gets sore too. And I lost my good coffee. I know. It's crazy. Do we need to do more of those? No. It was good, except for the fact that I had lost my coffee mug and I had to shovel 4 times because my snowblower broke. But I will say one of the good things about my weekend is that when I started to shovel, what was that, Friday morning when we had a ton of snow, I was out there shoveling and my neighbor, he saw me going out there and he has a 4-wheeler with a plow on it. He's like, Jeff, no. Take my 4-wheeler. I'm like, are you sure, Jerry? He's like, yeah. Please. I'm like, thanks, Jerry. Jerry's a great neighbor. Let me use his 4-wheeler to plow my driveway. It's awesome. I did. It's great. My kids were like, oh. And then now I want to buy a 4-wheeler. Oh yeah, I will use it nonstop. I will always be using it. Just exactly. So if I want to solve for x here, what happens? Yes, ma'am. The x is it's log base 9 of x. So x is 1. Okay. So it's tough to type these things in. So this is log base 9 of x equals 1/2. Now, in order to solve for x here, I have to rewrite that into that exponential form. And that's where a lot of the bases and the exponents where we change things back and forth allow us to do this. So this means I would have to write as 9 to the half equals x. And what's the half power? Well, yes, the answer is 3, but half power means you're taking what? Square root. All right. Not too terrible, is it?
Yeah, it looks great when you start explaining it. Yeah, and then the book just
So you're also gonna get a lot of stuff that is non-calculator based. So what you want to do here is you start thinking b to what power equals 81. So 3 to what power would equal 81? Yeah. How would you get that? Well, what's 3 squared? You're not going to get that. 9. If I do 3 cubed, I get, if I multiply that again by 3, I get 81. Or if you remember, as you start going through some of these properties, when you have an 81 and a base 3, that means it's probably going to be a smaller exponent. I mean, you'll start to pick up on some of these. Log base 5 of 4 hundredths. Well, if I wrote that as log base 5, 4 hundredths is 4 over 100, right? What would you simplify that to be as a fraction? 25th. So if you start thinking of it in terms of fractions as opposed to decimals, remember I've always said fractions are a lot easier to work with than decimals. 5 to what power gives you 1/25th? -2, excellent. Okay. All right. 1/2 to what power would equal 8? Close. -3. Okay. What's happening here is you're thinking, all right, this is 1/2 to some power is going to equal 8. Well, when I have a fraction and then I needed to make sure that I get a whole number, I'm going to raise it to a negative exponent. 2 cubed would be 8. So then I would say this would be the negative third power. Okay. The light just went on, didn't it? You did, didn't it? Right? See? It's not bad. Becky, what do you got? Oh, it's just saying what would the answer be? So you're kind of working it through your head. A lot of times when I do things like this, I'm writing it to exponential form because I'm thinking, right, 1/2 to what power is going to equal 8. And that's how I think through it. You just did this problem. 9 to what power equals 3? 1/2, excellent. Right? You can't do these to get you crummy numbers. All right, you can't do these in your head to get crummy numbers. You always have to be. They're always going to be clean. All right, because it just doesn't work. Yeah, it would equal that. Log base 9 of 3 equals 1/2. Because what you're doing here is you're taking this log base 3 of 81, and you're thinking, all right, 3 to what power is 81? That would have to be 4. So you're starting with this part, and you're figuring out that. You're figuring out what is the exponent that creates this. Oh, yeah, I don't need this one. Inverses. Yeah, well, we do a little bit of this. By definitions of log, it follows the function. Logs are functions. Okay. They are inverses of one another. And if you substitute in one for the other, in terms of log base b, if I wrote, all right, a composite, make this really easy right now. They undo each other. If you write this as log base b of b to the x, those two bases are the same. Okay? Those two bases are the same, so it undoes it, which means the exponent drops. And you're left with x. All right? I'll show you a numerical example here in a second. As soon as you have the same base with logarithms, it basically undoes itself. Okay? So if I wrote it as log base 3 of 3 to the x, those bases are the same. So the answer would be x. It would simplify to equal x. Same thing goes with if I wrote it as log base 3 of 9. What would that simplify to become? 2. Very good. 2. 2, because what can I do to this 9 to rewrite it as a base 3? 3 squared. So this becomes log base 3 of 3 squared, which equals 2. Logarithms allow you to do that. So you're going to see a lot of rewriting of bases to get the same base. Same thing goes for, excuse me, same thing goes for this. If we say if we have a base to a log base, this is a thing, yes. If those two bases are the same again, they undo each other. They undo each other. So if I have the same idea, if I have 4 to the log base 4 of x, that just means it's x. It's just another way of rewriting. When we go to solve equations with these things eventually, that's kind of called exponentiating something. When you raise it to a log base, it's a technical term for something that, as we get into it, it's bing, 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 and that means pressing buttons. They are, yes. This is the model before this one came out that actually made noise when you pressed it. Then they realized it wasn't a good idea to have that in school. Oh, I would be serious. One of the older models of the TIs actually pressed the big noise. It really kind of got annoying. Good luck. So, 10 to the log of 2. What's the base that you don't see? 10. So what's your answer? 2. How do you know that? And I know that because earlier I said that if you see just the word log, if I see log of 2, it's implied that it's base 10 if you don't see a base. If I don't see a base written below that, it means it's base 10. It's the same idea as that what's the coefficient there? 1. It's not there, but it's there. So that would equal 2. Now, same idea where I had log base 3 of 9 to the x. When I rewrite that as a base 3, I get log base 3 of 3 to the 2x. which means that would simplify to equal 2x. Jack, you don't look like you believe me here. Excuse me. Okay. You do a lot of quick simplifications to allow the bases to drop. Why is it 2x? Because what's 9? It's 3 squared. Yeah, you know, if you got here on time. All right. Figure those out. Log base 2 to 60. Log base 2 of 64 is going to equal what? Oh, come on now. 6. How? It's 2 to the 6th power. These bases undo one another, which gives you 6. Or if you start thinking of it in terms of rewriting your bases to exponential form, you get the same idea. Okay. Log base 25 of 5. That means 25 to what power is 5? To the 1/2. All right? If you get it that way, otherwise, if you rewrote, if I want to rewrite 5 as a base 25, I'd have to write it as 25 to the 1/2. See where I'm going with that? And it works the same way. You're undoing your bases, or you can go to your equivalency statement. It all works. Logarithms are crazy how quick they really are. Your answer is 1/2. Log base 6 of 1. Well, what's anything of log base? So it's got to be 0. Yep, it's got to be 0. Yeah, it's 10 to the log of 4. Why? No, it's 10 to the log of 4. It's 4. Your answer is 4. How? Because what is the base of the log you don't see? 10. This is 10. Yeah, according to the book of logs of laws and logs. Okay. There's also this thing called the natural log. So it is the log of the natural base. There's a button on your calculator that says ln, log of the natural. That's where E stuff comes into play. So you've got logs, and this goes back to the idea of when you see log base 10, it's just written as log. Now, you can have base of anything. So if you have log base E, it stands for natural log. Just another way of writing it. Log base E, it's the log of the natural. It's just the way they write it. If you have base E, it's just another way of writing it is natural log. Okay. So those two mean the same thing. Okay. Common log is just base 10. Drugs? I don't know. Growth hormones? I don't know. Alright, I'm not going to graph them today. Well, actually, we have time. Let's graph. Graphing. Well, look. Now, when you graph logs, It is not too much. When you graph logs, they are also when we graphed exponentials earlier, there was a little bit more work involved because you had to do -2, -1, 0, 1s, and 2s to be able to make them work, and you got your 5 points and you shifted them. When we do these with logs, there's a little bit less work. Right, so when we have logs, log base, what did I write this? I forgot. Log base b of y is x, so b to the x is y. So when we go to graph them, you have your log base b, x minus h, plus k. Hey, what do you think the h's and k's stand for? Horizontal and vertical shift. Okay. Now, you will always have vertical asymptotes at h. At x equals h. And your domain is x is greater than h. Excuse me. And there's only two ways that these graphs go. It's either going to go up and right or down and right. And that just is dependent upon the base. So if your base is greater than 1, it's going to go up and right. And if the base is between 0 and 1, it goes down and right. But what's crazy about logarithms is that you really only know 2 points that'll make it work. And that's why I figured, even though that you guys are, graph, this sucks. What you're trying to do here, besides get out of doing work, is you're going to use some very easy properties to get easy points. We're going to use easy properties to get easy points. That way you know how things are shifted and moved. Excuse me. So, if I go through and I start with this. I start with this one. Log base 1/3 of x minus 1. What's your HK? What's your HK? Have a problem. Your H's will always be thrown in with parentheses. I don't see parentheses. So your H is what? H is 0. Your H value is always going to be in parentheses. Your H is always in parentheses, your K is not for these. It's been like that all along. I've only said it once or twice. Maybe. I don't know. Pretty sure. Okay. So your H is 0, your K is -1. Your B value is 1/3. Now, that means what direction is this going to have to go? Down and right. So I know no matter what, my graph is going to look something like this. But it's just telling me where it's at for right now. But what I do now is I'm going to try and find myself some really easy points to start with. Careful. Excuse me. When you start looking at this, you want to think about the real easy properties of logs. Log base b of 1 equals what? log base anything of 1 equals what? 0. And then log base b of b is always equal to 1. Okay. So you're going to use these properties to create your ordered pairs. I use those properties to create my ordered pairs to make it work. So what, excuse me, if I use 1 for x, log base 1/3 of 1 equals what? Well, any log base of 1 always equals 0. Okay? So I know that if I choose for an x value of 1, I get log base 1/3 of 1 equals 0. Okay? I'll shift this in a second. So just here gives me my first ordered pair, 1 and 0. I do the same idea if I use 1/3. What's 1/3? What's log base 1/3 of a third? 1. I use log base 1/3 of 1/3. It's 1. So that would be my other ordered pair. You okay with that so far? I'm looking at my parent function here. My parent function is log base 1/3 of x. My shifted function would be log base 1/3 of x, subtract 1. So at 1/3, it's 1. Well, I know that I have a vertical asymptote where? Vertical asymptote at 0. Because you have a vertical asymptote at h, and my h value here is 0. Okay, so I have a vertical asymptote at 0. Where's my... Oh, there it is. I have a vertical asymptote at 0. Right. I have ordered pairs. Here's 1/3 and 1. And it's doing this. I haven't shifted, that's why I did dotted. Yes, sir. Sir. Yeah. I haven't done the shift yet. Remember I said I'd do the parent function? There you go. So with those being, when you're working with logarithms and graphing them, you're only going to graph 2 points, and then you plot your asymptote. Your 2 points will be whatever the base is, and then the other point would be at 1. You're using those values. And then from those generates your ordered pairs for the parent, and then you just shift them. So for these ordered pairs to get shifted, all I have to do is just move them down 1. So the shift would be at 1, -1, and this would be at 1/3 and 0. So 1/3 and 0. And then here's my... When you're graphing, all you have to worry about, bless you, all you have to worry about for your graphing is going to be 2 ordered pairs. Your 2 ordered pairs are going to be the ones that fill in this. Whatever the base value is, and 1. So for every parent function, you're going to use an x value of 1, and you'll use whatever the base is. Okay. Do one more real fast. Log base 5, just to show you what you would choose. Just real quick for your parent function. That's your parent function. Oops. Dang it. What are my two ordered pairs I'm going to pick? My parent function, I'm going to pick 5 and 1. That's what you're doing. Because what's log base 5 of 5? 1. And what's log base 5 of 1? 0. There's your ordered pairs. Shift. It's that quick, guys. It's literally that quick. So this is on 8.4. I got to post the PDF, so Carter don't yell at me. Let's go 24. I'm sorry, 20 to 34 even. 48, 64 even, and 66. We'll just start with those. What's that? Yes. 2 points. 2 points, because then you shift off. All right. We'll start with those. We'll shift and go. I'll get that PDF posted to it probably during the passing period. Okay? Yeah, quick. Yeah, send me an email. Yeah, right. Well, for this one, if you substitute in, this would give you a parent function. If I put in 5 for x, log base 5 of 5. 1. So my ordered pair would be 5, 1. And the other one, if I do log base 5 of 1, I get 1 and 0. So those would be my 2 points. I know where they're going to go. I know where my asymptote is for that problem because I had it for the parent function. It has an asymptote at 0. The shifted one will have the asymptote at h. That's why you just move it over.